Now, week 4 lecture, we still study planar kinematics of a rigid body. In week 4, we study how to use relative motion analysis to do acceleration analysis on general plane motion. We will study the translational and rotational components of acceleration of a point on a rigid body undergoing general plane motion. And we will use relative acceleration analysis to solve some problems. But in this week, these problems are about links. Another kind of problem is roll without slip motion. And this kind of motion is a very important topic. And we will present this in next week. Now let's look at mechanism. This mechanism is applied in automotive engine. And here you can see a piston and you can see a connecting rod, and here there is a crankshaft. This crankshaft is rotating about its fixed axis through point A. Piston is undergoing a rectilinear translation. The connecting rod is undergoing general plane motion. Let me show you the videos. The first video is about a two-stroke engine.
Engine is a type of internal combustion engine which completes a power cycle in only one crankshaft revolution and with two strokes, or up and down movements, of the piston in comparison to a four-stroke engine which uses four strokes. There are usually three ports: an inlet port, exhaust port, and a transfer port. The transfer port connects the lower chamber beneath the piston to the upper chamber above the piston. The first stroke of the two-stroke petrol engine begins with the piston about halfway down the cylinder heading toward the top of the cylinder, going upwards. Because the piston is halfway down the cylinder, all of the ports are covered. Because of the upwards motion of the piston, the bottom chamber below the piston falls below atmospheric pressure. As the piston moves closer to the top of the cylinder, it uncovers the inlet port, which then, because of the pressure in the lower chamber, sucks air and fuel into the lower chamber.
The second video is for a four-stroke engine.
Internal combustion engine is used in motorcycles, automobiles, boats, trucks, aircraft, ships, heavy-duty machinery, and power generators. A four-stroke engine is an internal combustion engine in which the piston completes four separate strokes: intake, compression, power, and exhaust during two separate revolutions of the engine's crankshaft and one single thermodynamic cycle. Let's take a look at the basic internal parts of a four-stroke engine.
Whatever two-stroke engine or four-stroke engine, and you can see in the videos the mechanism same. There is a piston, connecting rod, and a crankshaft. Now, how can we get the relationship between the accelerations of the piston, connecting rod, and crankshaft? And this problem can be solved using relative motion analysis on acceleration. Okay, now let's see how we can work out the equation for relative motion analysis. We used this slide before when we studied relative motion analysis of velocity. In this one here, we have two coordinate systems. One is x, o, y. This one is fixed. And another coordinate system is x prime, a, y prime. And this one, its origin is at point A in the rigid body AB. This coordinate system can translate, but it's not allowed to rotate. Here, rigid body AB is undergoing general plane motion, moving from its initial position to its final position. We already know we can resolve this general plane motion into two motions. One is rectilinear translation from AB to AB prime. The second motion is rotation about point A. Fix point A, rotate from AB prime to AB. Okay, now look at the displacement of point B, displacement of point A, and the displacement of point B with respect to point A. Here we can see the three vectors, their relationship will be like this. And here, this one, this is due to translation and rotation. And this one is due to translation about point A. And this one is rotation about point A. Now, if we do time derivatives on both sides, on left side, it will be drb dt. This will give us vb, the velocity at point B. On the right side, for the first item, we will get dra dt, that will be va. And the second item on the right side will give us VBA. VBA is the velocity at point B with respect to point A. And this item, VBA, can be expressed using the angular velocity of this road AB cross product, the vector RBA. So, in this equation for relative velocity analysis, if we take point A as the base point, then for velocity of point B, it has two components. One is translation component of this velocity is equal to VA, and another one is rotational component of velocity. This is VBA. Okay, next, if we can do a second time derivatives on both sides. On the left side, it will be dVB dt. This will give us AB, the acceleration of point B. On the right side, the first item dVA dt will give us AA, and this will be the acceleration of point A. This item dVBA dt, this will give us the acceleration of point B with respect to point A. That will be ABA. This ABA has two components. One is tangential component and another one is normal component. This one tangential, this one normal. So you can see for acceleration, as similar as that for velocity, we have two components. One is translational component and another one is rotational component. In this rotational component, we have two components. One is tangential and another one is normal. Now let's look at the rotational component. This one is from the rotation about axis through point A. For this one, based on our study in week 1 on rotation about a fixed axis, we know at point B, when we look at its acceleration, there should be two components, and one is tangential and this one is direction. It's always tangent to the moving path of point B. Another component is the normal component, and this one is direction is always opposite to the direction of vector RBA. Vector RBA is direction is from A to B, but for this normal component, its direction is always opposite. For tangential component, it can be calculated using the angular acceleration of AB cross product vector RBA. For the normal component, it can be calculated using omega square times RBA vector. For this one, because the direction of this normal component is always opposite to the direction of vector RBA. So before this item omega square RBA, before that we always have a negative sign. Finally, we can get the equation for relative motion analysis on acceleration here. And this is the only equation we can use for relative acceleration analysis. Okay, now let's have a look how to do analysis of acceleration on a problem like this, and this is the link problem. And here we can see a road AB. This one is undergoing rotation about a fixed axis through point A. And the piston, rectilinear translation. Link BC is undergoing general plane motion. Okay, so focus on this link BC. Of course, for this one, as similar as what we did in velocity analysis, we need to select 2 points. For this link BC, the 2 points should be B and C, because these 2 points are pin connection points. For point C, its acceleration should be as same as the point C's acceleration on the piston, because piston is undergoing rectilinear translation, so the acceleration of the piston must be horizontal. So at point C on link BC, the acceleration should be exactly same. It's horizontal. But how about point B? Why the acceleration of point B, its direction should be like this? How can we get this direction? Let's look at link AB. Link AB is undergoing rotation about a fixed axis through point A. So at point B, we know its acceleration must have 2 components. One is tangential component, another one is normal component. For normal component, its direction always from B to A. For tangential component, its direction must be tangent to the moving path, the circular moving path of point B. Because in this one here, you can see the direction of angular acceleration alpha is clockwise. So here, ABT, the tangential component, must be to this direction. Okay, now the resultant acceleration at point B will be like this. This is from the normal component and the tangential component. Next, here there's a different problem. In this one here, 2 rigid bodies contact with each other. And actually you can see this one here, 2 gears. As mentioned before, we normally assume between 2 engaged gears, no slipping. Okay, now in this one here, I have 2 questions. Here, A is on gear B, A prime is on gear C. At this moment, A and A prime, they are actually one point, the contact point between these 2 gears. Question here is, for the velocities at point A and velocity at point A prime, these 2 velocities should be same or not same. Another question here is, the accelerations at point A and A prime, they should be same or not same. For velocities at A and A prime, this should be easy to answer because no slipping between two gears. So at point A and A prime, the velocities must be same. If they are not the same, then slipping occurs. But we already assume no slipping. But how about acceleration? For acceleration, the analysis will be a bit difficult. And here, please note the contact point A prime. Here, there is no pin connection between two gears. So for point A, here for point A, there should be two components of its acceleration. One is normal component AAN, direction from A to the rotation center of this gear B. Another component is AAT, the tangential component. For A prime, its acceleration also has two components. One is normal component, direction from A prime to the circle center of this gear, C. And another one is a tangential component. For this tangential component, AAT and AA prime T, these two should be same. For normal component, AAN and AA prime N, these two, obviously you can see they are not the same. Not only magnitude, but also directions. Obviously, their directions are opposite. So finally, this will result in a direction of AA and a direction of AA prime. They are not the same. Okay, next, we can use this relative motion analysis of acceleration equation to solve some problems. For these examples, I will do analysis and I will present kinematics diagram, but I'm not going to explain the calculation process. The calculation process in relative motion analysis, you know, it will be vector calculation. We have already started this in week 2 when we do relative motion analysis of velocity. So you should be already familiar with the calculation process. Anyway, if you have any questions about the calculation process, about the vector calculation, please let me know. In this first example here, you can see one road, AB. AB is confined to move along the inclined planes at point A and point B. And here we already know at point A there is an acceleration of 3 meters per second square. And also we know the velocity at this point A. The instant we are studying is when this road AB is horizontal. Okay, so it's easy to define. AB undergoes general plane motion. Now, kinematics diagram. This is AB. At point A, we already know its velocity, VA, and its acceleration, AA. The angle between VA and AA and road AB, this angle is 45 degrees at this instant. Now another point, point B. By observation, we can reasonably guess the direction of VB and AB. The direction of VB and AB indicated here might be wrong, but it doesn't matter. In the very beginning, we can assume VBX and VBY, they are positive. We also can assume ABX and ABY positive. So this will give us the direction of VB and AB like this. Because point B is as similar as point A. So at point B, the direction of VB and VA, and AB must be parallel to the plane. For angular velocity omega AB and angular acceleration alpha AB, we just assume they are counterclockwise positive. Why? Because here I established a very conventional coordinate system, and in this coordinate system I defined counterclockwise is my positive rotation direction. Then I can list the already known parameter AA. AA is the vector because vector calculation will be involved, so I express AA in a vector form. Also VA. VA is 2 meters per second, and I can express VA using a vector form. Okay, the target is acceleration. The only equation we can use for this acceleration analysis is this one. And here, 2 points, B and A. And here in this diagram, B and A. And A is our base point. In this equation, we have alpha AB. Alpha AB at this moment is unknown. We have omega AB. Omega AB at this moment is also unknown. So for acceleration analysis, normally before we can solve acceleration, we have to work out velocity firstly. For example, here we have to work out omega AB firstly. How to work out omega AB? Of course, you can use relative motion analysis of velocity. we studied in week 2. But in week 3, we studied IC method. As suggested, if it's possible for velocity analysis, we can always try IC method firstly. Okay, here in this diagram, you can see we know the direction of VA. We know the direction of VB. It must be parallel to the inclined plane. So I can draw one line going through point A and perpendicular to VA. I can draw another line going through point B and perpendicular to VB. These two lines have an intersection point, and this intersection point is the IC point at this instant when road AB is horizontal. Using trigonometry, it's easy to find the distance from A to AC. From A to AC. Because we already know VA, so we can just simply use VA divided by the distance from A to IC to work out omega AB, its magnitude. And here you can see the IC point is above the road AB, VA to this direction. So this means the angular velocity omega AB of this road must be counterclockwise. After getting angular velocity omega AB, we can substitute it into the equation of relative motion analysis of acceleration. Using this equation, on the left side, we express AB using ABX and ABY. On the right side, for AA, we express it using AAX and AAY. These two can be easily worked out. And here, alpha AB, we don't know. As mentioned before, we just simply assume they are positive. So this is alpha AB vector K. RBA. RBA, look at this diagram. RBA, the direction from A to B. AB is horizontal. So vector RBA should be equal to tan I. The last item, omega AB, has been worked out. Substitute it here. RBA tan I. Okay, now we do vector calculations on the right side. From here to here. And then we combine all items before I along X direction. We combine all items before J along Y direction. Then we compare these vector equations, both sides. So ABX must be equal to this item, and ABY must be equal to this item. Now, the problem here is we have ABX, ABY, and alpha AB, three unknown. But we have only one vector equation. That means finally we can have only two scalar equations. That means we can only solve only two unknown parameters. But here, three unknown. So this means if we can't do something, we can't solve this problem. But here, if you look at the diagram, look at this AB. Its direction can be determined easily because AB must be parallel to the inclined plane. So this means the angle between AB and this road AB, this angle must be 45 degrees. And that means ABX, ABY can be expressed using AB. So this means finally we only have two unknown parameters. One is AB and another one is alpha AB. So using these two scalar equations, we can work out our final answer. AB can be worked out and alpha AB can be worked out. And here you can see in this final answer, alpha AB is positive. That means initially in the kinematics diagram, the assumed direction of alpha AB positive. That's correct. Okay, you know alpha AB is acceleration, it's a vector, so we must indicate its magnitude and direction using a vector form. Everything will be very clear. In the second example here, we have road AB undergoing rotation about a fixed axis through point A. We know its angular acceleration, omega AB. It's counterclockwise. For course C, this one is undergoing rectilinear translation, so the motion must be vertical. And here, we already know the direction of AC and VC. Both of them are downward vertical. CB is undergoing general plane motion. For this one, we already know its angular acceleration, omega CB, is counterclockwise. The target here is to determine the angular acceleration of CB and AB at this instant. One AB is vertical. Okay, angular acceleration is a vector, So this means we need to determine both the direction and the magnitude of alpha CB and alpha AB. For the directions of alpha AB and alpha BC, is it possible to determine their direction by observation? It seems possible, but actually it's not reliable to determine the direction of acceleration by observation in most cases, including the directions of alpha AB and alpha BC here. This is different from the direction of velocity. For velocity, its direction, in many cases, you can determine by observation. But for acceleration, it's quite different. Okay, now look at the kinematics diagram. Again, here, for this acceleration analysis, because vector calculation will be involved, so I need a coordinate system. And here, I use a very conventional coordinate system, and here I define positive rotation direction is counterclockwise. Firstly, for link AB. For link AB, at this instant is vertical. The direction of omega AB is already known, so this means the direction of VB can be easily determined. It should be horizontal to right side. Its acceleration, angular acceleration alpha AB at this moment is unknown. We just simply assume it's positive counterclockwise. So we should be able to indicate the direction of its tangential component of AB. It should be as same as the direction of VB. The normal component of AB is always from B to A. A is the rotation center. Now we look at link CB undergoing general plane motion. For this one, at point C, C is the pin connection point between link CB and the collar C. The collar C, its acceleration and velocity both are already known. They are downward vertical. So this means at point C on link BC, the velocity and the acceleration VC, AC, both of them should be vertical downward. Now, point B. Point B, if we only look at link BC, we don't know anything. But B is the pin connection point between BC and AB. So that means we can copy everything from here to here. ABN, vertical upward. ABT, VB, these two, horizontal to right side. For the direction of omega CB, this one already known counterclockwise. For the direction of angular acceleration alpha BC, for this one, we don't know at this moment. We just assume it's counterclockwise positive. That's the kinematics diagram for solving this problem. Okay, now the third example. And in this mechanism here, a wheel, a disc, is rotating about its fixed axis through point. Here, a color A, it has a rectilinear translation, and this is horizontal. Between this color A and this disc, there is a link AB. This link AB is undergoing general plane motion. And here, we already know the angular velocity and angular acceleration of this disk, both magnitude and directions. The target here is to determine the velocity and acceleration of color A. Now, the kinematics diagram. Again, vector calculation will be involved. We need a coordinate system, and it's here, a very conventional one. Counterclockwise has been defined as the positive rotation direction. Okay, now, if we look at link AB undergoing general plane motion, we can see point A and point B. These two are pin connection points. So we can use these 2 points to do our analysis. At point A, because this is the pin connection point between AB and the color A. The color A has the rectilinear translation horizontally. So that means at point A, the acceleration AA and velocity VA, both of them must be horizontal. We don't know its direction, right side or left side. At this moment, we just assume they are positive to right side. But how about point B? For point B, this is the pin connection point between this link AB and the disk. So we will look at the point B in the disk firstly. And you can see here, this disk is undergoing rotation about its fixed axis through point. This through point is actually its circle center O. Okay, we already know alpha D, we already know omega D. Both of them are clockwise. So if we look at point B, we can find at this point, VB must be perpendicular to a line connecting B and O. Because omega D is clockwise, so VB, its direction must be upward instead of downward. For acceleration at point B, 2 components. One is normal component this direction must be from B to O. Another one, tangential component. For this one, because alpha D its direction is clockwise, so this means the direction of ABT should be as the same as the direction of VB. Now, we can copy everything from this point B in the disk. To the point B in link AB, including the direction of VB, direction of ABT, and the direction of ABN. All these are exactly as same as those shown in the kinematics diagram of the disk. Okay, here you can see we already know omega D, we already know alpha D, both of them are negative according to this defined coordinate system. We already know VAY and AAY. Why? Why they are 0? Because at this point A, VA and AA, they must be horizontal. So this means their components along y direction must be 0. We don't know VA, VAX, VAY. We don't know AA, AAX. We don't know omega AB. We can assume they are positive if we use relative motion analysis by vector calculation. Okay, here, that's the idea for solving this problem. We know alpha D, so we can work out ABT. We know omega D, so we can work out ABN. If we know these two components, that means we can work out AB. AB in this equation for relative motion analysis of acceleration. Here, B is the base point. In this equation here, AAY is already known, only AAX is unknown. So that's one unknown parameter. Alpha AB is unknown, so that's the second unknown parameter. Omega AB at this moment is unknown, but it can be easily worked out using relative motion analysis of velocity. Because we already know omega D, the angular velocity of disk, so we can easily work out VB. In link AB undergoing general plane motion, we know VB, we know VAY is 0, VAX is unknown. So if we use relative motion analysis of velocity, we can easily work out VAX and omega AB. Then substitute this omega AB into this equation for relative motion analysis of acceleration. we should be able to solve alpha AB and AAX. For this velocity analysis, it's not necessary to use relative motion analysis. As mentioned, you actually can use IC method to solve omega AB. Following will be the vector calculation. For this calculation, I'm not going to give detailed explanation. So firstly, this is velocity analysis, relative motion analysis of velocity. But if you don't like this method, you of course can use IC method. Then we work out AB. Then we work out omega AB. Then finally, relative motion analysis of acceleration to work out alpha AB and AX. For this vector calculation, if you have any questions, let me know. So that's all for week 4.